Okay, here's our setup for our experiments on momentum. And if you take a look at, you probably have seen in your booklets that we're looking at this experiment first, which is called explosions. The setup is fairly straightforward. You have two carts together, and at the tap of the top of one of the carts, it's going to release a spring and push these two carts to either side. So we're starting from completely stationary positions, and they bounce apart. They explode, in fact. So here are our two carts. You can see the mechanism here, that when this is depressed, that jumps out, and we're going to place it back in. And a simple method to kick it off will be just to drop a weight in it, and it will bounce off. Okay, so that's our setup with explosions. But before we really go any further, we need to work out, because you're probably fully aware of the ideas of momentum now, how fast these objects are moving. So what we have here is we have a light gate. And as our trolley, with this mask, moves through the light gate, you'll probably see here the light go off. It has an ability, this machine, to time how long this obstruction has gone through the light gate. And if you know how long it's in the light gate for, then if you know this distance, the distance of this divided by the time it's in the light gate will give you a speed of that trolley, assuming that it's moving at a constant speed, which we are assuming, because this is nice and frictionless. So that machine there will either tell you the time in the light gate, or it will directly interpret that into a velocity, I should be saying technically, a velocity, if you tell it how wide this mask is. So let's just see how you would do that. You have the systems here, and it says select mode S. You press S, has time interval, you press it again until it says speed. Enter, this button, D. Select a number. Well, we press S. We're looking for two readings, because you want this light gate and then that light gate in all of these. D. Mask size. How wide is this? That is actually 10 centimetres. So you keep pressing S, and you'll notice that the number on this side increases. Keep pressing S until you get to 10. Enter. Press go when ready. So we press go, and when we run the experiment, if this one were to go through there, that were to go through there, it then changes to say display. You get one velocity, press again, the next velocity, press again. It gives you an option, you're ready to go again. And so you get multiple readings that way. Okay, excellent. So that's how the light gate works. We've got obviously the trolleys here, and we have the ramp, which has been adjusted at the far end. There's a small little screw at the far end to raise or lower and make sure this is as flat as possible, which is really important, because we don't want anything to affect this other than the explosion that takes place in the spring in the middle. Okay, you're given different setups here. You're asked to look first of all at what happens when you strike this and you have even masses on both sides. These are both 500 grams, hence 0.5 the kilogram. We then, in experiment B, change it by placing a 500 gram mass on the second trolley to see if that's going to change the velocities of these. And then finally we place 150 grams, i.e. two 500s plus the 100, plus the, two 500s plus the 500 of the trolley, making the whole of this 150 grams, 150 grams, or the 1.2 kilograms. Yeah, 500 grams, 1 kilogram, 500 grams, 1.5 kilograms. Excellent, so let's just run those through, get some figures, and then we'll start analysing and seeing what happens. So we'll take this out. Got that well balanced, just make sure it's all aligned. And then with this, we merely strike the tops. Watch out, this one doesn't fire off one side. Good. It only takes the once through the gate, so even though it's bounced back, that's not a worry about. And then we hit display. It says 5.1 meters per second. So 5.5 meters per second and 5.0 7 metres per second with the velocities. Now bearing in mind one shot that way and the other shot that way. So if we need to take a direction to be positive. So let's imagine this is positive for our velocity, and that must mean that the 5.5 is actually minus 5.5, and this is plus 5.7 because vehicle 2 went that way, vehicle 1 went that way. Okay, straight away, let's change the masses. Bring this back together again, reset. Extra mass on this side. Hopefully out of the way. Place these together. They just stick together because there's a very small bit of Velcro on these parts. Display. One more time. It gives you an option GSD, ready to go. G, then. Oh, need a bit of compensation there. Good, you notice this time, and hopefully you would have worked this out anyway, that this one moves away slower because it has a greater mass. This one moves away faster because it has a lower mass. Let's see if that's right. We have initially 0.99 and 0.49 minus. One went that way, the opposite one went the other direction. Okay, let's try it one more time, but this time we're going to increase to 150 grams. Sorry, 1,500 grams, I keep saying that wrong. This is going to be 3 lots of. Reset, reset, press together. Press display again, G, back to where we started. It's waiting for its set of results, so if I can dexterously get that, then we will. Good, much slower, much more mass. Let's see what we've got. So, apparently the first one moved away at minus 0.86. The other one moved away at 0.36. Okay, so what it's now asking is, you know the momentum of this cart, and you know the momentum of that cart, because you're merely multiplying these two values together. Multiplying and multiplying. Similarly on this side. So, does the momentum, those two multiplied together, get close to these two being multiplied together? And that's what it's asking you to work out below. So very simply, let's have a look. Total momentum before the collision. Well, that's not moving, so the total momentum before is 0 in all of these experiments. The total momentum afterwards requires a bit of calculation. Just quickly work those out. We have 0.5 by 5.5 gives us 2.75. Be careful to keep note of those minus signs. They're important because it's a velocity we're dealing with. We'll have 0.5 by 5.07 on this other side. 2.54. And the total will be the addition of these two afterwards. And because one's minus and the other one's positive, we're hoping they cancel out because the total before must be equal to the total after, ideally. So minus 2.75. Okay. So the difference is very, very small. Let's try with the next one. This is minus 0.495. 0.49, really multiplied these two together, and the difference there is minus 0.005. Tiny difference. Last but not least, 0.435. minus, because it's going that direction. This one was 1.5 by positive 0.54, giving a difference of 0.11. Okay, so hopefully you can see that though there was zero momentum before the collision, afterwards there was some, ideally there shouldn't be, but it's very, very small. And we can account for those differences by things like friction on the track, whether it's completely flat or not. But I think that's in good agreement. The momentum before the collision equals the momentum after the collision. If you need the results, jot those down. However, we're going to be moving on to looking at collisions. So the second part is looking at collisions this time. In other words, we're looking at a stationary object without the springs, so we put the springs away, a stationary object, looking at an incoming object, and what velocity they're x'd with whilst joined. This is actually called an inelastic collision because they join and coalesce afterwards, but the conservation of momentum should be the same. The incoming momentum of this object should be the same as the outgoing momentum of both of those objects. So let's try it. We have the table that we need to fill in. We're looking at experiment 1 that looks at equal masses. Then we're having experiment 2b, which looks at 3 times the mass of the colliding of the object that's stationary, and then the reverse. The incoming object has 3 times the mass. And we'll get some values and see what the momentum before and afterwards is. Okay, this is all set up, so that's ready to go quite happily. We're looking to have equal masses. Ready to go. Okay, they both moved away slower than the incoming one because they have a greater mass when coalesced. Let's look at the speeds. 0.5 is my incoming speed. This time it's positive because this is my positive direction. And my next speed was 0.242, with 2 lots of 500 giving us 1 kilogram. Okay. We're now loading up to have 3 times the mass of the stationary object. Display, go. And let's see how fast it exits after being collided with. Okay, incredibly slowly. Let's see whether, and of course at those speeds friction has a much bigger effect. Incoming speed of 0.527, I'm fairly consistent with how I'm pushing it across. Outgoing speed at 0.114. And a combined mass this time of 2.00. Okay, we'll do the sums in a moment to see whether the conservation of momentum is holding true. First of all, we're going to reverse this around. We're going to place 3 times the mass on the incoming object, and the stationary object is the normal 500 grams. Okay, display again, go. That's stationary. It's going much faster this time afterwards because this doesn't add very much mass at all to it. Most of the mass is in this one. Let's see what we have. Pushed it a little bit slower. The knowledge of that. 0.462. Exiting speed at 0.342. Not much change in speed. And of course the mass is again the addition of these two. So let's see if we have a conservation of momentum going on. Simply what we're going to do is we're multiplying these two together to get the momentum before the collision, and we're multiplying the combined mass with the new velocity to get the momentum after the collision. So the momentum before, plug these in, it's going to be 0.5 by 0.5, 0.255, positive because it is moving that direction. The momentum afterwards is going to be 0.242. Now I'd say that is approximately equal. I think that's pretty good agreement there. Okay, the next one down. Let's multiply the second column down and see whether it's the same as the combined mass by the combined velocity. (0.264). Let's see if it equals 0.228. I'd say that's in pretty good close agreement. And finally, last but not least, momentum before, so we're multiplying this last column together and seeing whether it equals the combined mass by the combined velocity. 0.693, and is that equal to 2 lots of 0.342, 0.864. I think those are in very close agreement and show that the momentum before the collision equals the momentum after the collision pretty closely. Okay, I hope that all makes sense.